for quiz 1, there are 2 voltage supplies that are contributing to the same voltage node at the same time. So for superposition, you just take in one consideration each time and short the other one to ground. Here's V out. So the voltage of V out is comparing to the ground. So the first time the V1 when we are doing V1 only, R1, R2. So V out equals V1, V1 times R2 over R1 plus R2. So when we do V2 only, we short V1 to ground. It's still the same voltage node. We're not changing it. So there's not making sense to make it adding a negative sign in front of it, right? Still the same node. And compared to ground. Why compare to ground always? All the voltages are relative. It's not absolute values, right? So if you don't want to measure, you want to tell what the voltage is in real life, you have to get 2 probes from the multimeter. Okay, so it's actually comparing the voltage in between these 2 probes. So it's relative. You have to put one, the black one, to the ground, and the other one to here. And if you change the black probe, the location of the black probe, or the reference to a different location, for example here, you're not getting VL anymore. So it's not VL anymore. So for example, if I probe it like this, the 2 probes, here's the red one, here's the black one, I do this, okay, am I still probing VL? No. That's why I want to go through this one more time, because I feel there's some confusions on it. When we are talking about VL, it's absolutely just that point at VL compared to ground. Okay, the node voltage is that voltage at that point compared to ground. It's not the voltage here compared to somewhere else. So this is not VL anymore. So what is the voltage here? What's the voltage if I do this, probe this? It's it's VR2. It's a voltage dropped across R2. Okay. Only I do this, I'm measuring VL. So in this case, here V2 only, VL2, this is VL1, VL2 equals V2 times what? So R1 on the top, R1 plus R2. Make sure everyone is getting 100 if you see this again in the future. It's just so boring. I probably don't put this in those exams in the future, but are you going to get 100 on this if I change the form of it a little bit? For example, if I add another one, okay, are still able to do it. R3, V3. Just do it 3 times, okay? And when you are, for example, doing V2 only, you short these two sources to ground. I got 2 parallel resistors. I'm going to combine these 2 parallel resistors as one, convert into 1, and then it's a voltage divider serial again.
So why is when you short V1 to ground, the problem that was on the quiz, short V1 to ground, V2s, why don't you add them together as V2 not negative, the opposite of polarities?
It's not opposite polarities, because we're always looking at VL, right? It's always this node. It's not changing. It's still that same piece of wire. Still the same wire. I hope I got where you are confused at.
I was thinking of VL.
Yeah. Okay. Because it's always this piece of wire compared to ground, so that's why it's always plus minus. Right? Right? See if I can find out the R2R. For the op-amps. Yes, I have to do this one more time. So for the op-amps, we just started the topic on Friday last week. You'll see this on quiz on Friday. So VP, VM, for example, VM now is 2.5 volts, and this is 5 volts, and this is ground, okay? This is V out. I'm just repeating this because sometimes it can be confusing because you cannot see what is inside the op-amp, just a triangle shape. So we should know or memorize that VP minus VM times what? Times open loop gain equals V out. And open loop gain is huge. Ideally, it's infinity. But we are only supplying 5 volts and ground, so the maximum voltage is 5 volts and the minimum is ground or 0 volts. So it's not going to reach the plus infinity and negative infinity at all. So it's going to saturate at 5 volts or 0 volts. So if I have a VP, so VM is here, which is 2.5 volts, and VP is changing like this. It could be different, but I'm just giving you an example, right? So VP is changing like this. So for example, if I give you a different signal, this VM, and different signal like this, right? You should be able to find out VL as well. Okay, and this happens a lot for the IR sensor on the robot car. The signal is not exactly triangle wave. It could be an arbitrary analog voltage like this. Okay? And then, for example, let's do both. Okay, so the triangle wave is what? Is which one? One more time. So the triangle wave here is which input? VP. Is there anybody else getting that? Why is VP? Because I labeled VM as 2.5 volts already. You got another input, which is VP. So VP is changing, is varying. So VP minus VM, if VP is larger than VM, you are outputting a 5 volts. If VP is less than or smaller than VM, you are getting a 0 volts because of the huge open loop gain. If VP is only slightly larger than VM, because the open loop is huge, multiplied by the infinity number here is going to amplify a lot and give you a positive infinity. However, the circuit can only supply 5 volts. It's going to saturate quickly, very quickly, to 5 volts. If VP is a little bit slightly smaller than VM, right, you are getting a very tiny negative number here and times a huge gain. So it's still going to reach a negative infinity. However, your circuit only supplies 0 volts as a minimum, so it's saturated at 0 volts. Because that's how that works. So if you have VP works like this, here is VP smaller than VM. Here's VP, right? VP is smaller than VM, and you're expecting a 0.5 volts for the output. Here, what about here? 0. Then, are getting that? Because VP is smaller than VM, so you are getting a smaller negative number here times a huge gain. It's going to saturate at 0 instead of, because it's going downward, right, to the 0 voltage direction. So here you're getting a 0 volts here, and when VP is larger than VM, you get a small positive number here times the gain. It's still going to be a positive huge number, but saturated at 5 volts. Okay, so we'll do this. Right. What about this one? VP, here's VP, here's VM is 2.5 volts in the middle, and this is VP. Definitely here is going to be 0 volts. All right. Did you get 100 points on the quiz on Friday? Yeah. Sort of forgot which resistor is R2. Let me take a look. Okay. Quick review on the superposition there. Okay. Well, this one, R2R deck, and the input is 101. So this, which one is LSB, which one is MSB? This is LSB. So this is D0, this is D1, D2. What? Yeah. So how do we calculate VL using superposition? What's the first step? So D0 only, right? D0 only. So these are all zeros. And this part becomes what? Yeah, we still use VDD to keep it consistent. So 1 is VDD, all right? Is 1. So this is a voltage divider. Power supply supplies the voltage from here, or through here, right? You got a voltage divider, and this is the output node. So convert into its Thevenin's equivalent, and you're getting this is RTH, which is half of the R, 2R, which you're looking backwards. You short these two, you got a 1R. So it becomes 1R. This is VDD over 2. So just use this one, replace this part, and then make the connection to the rest. This is, they're all zeros. And this is 2R here. And combine these two for its Thevenin's equivalent, and you're getting VDD over 4 and 1R here for this part. Okay, and then connect this one here. And this is 2R, and combine these one more time, and you're getting VDD over 8. And 1R here for this part, right? Wait, yeah, for this part. Is that correct? No, you are done. Is that correct? Don't have to do it one more time. So this is VDD over 4, you got a 2R, is a voltage divider. So VL directly equals VDD over 8. Yeah, because you are here now, right? It's already shorted ground. And this is 2R. This becomes this. 2R, ground. This is VDD over 4. 2R, right? It's the same circuit. So voltage dividers we are getting VDD over 8. So one LSB is contributing VDD over 8. And you are looking at the other part because you got a 1, 0, 1, so this voltage is also, D2 is also contributing something to V out. You cannot ignore it. But when you do a D2 only, the circuit becomes you got a VDD here, but all these are ground. So it becomes this if you are doing D2 only. So must have a question, for example, why superposition works. Why can't we just analyze each source each time and short all the other sources to ground? Yeah.
Why do you need to use superposition? I guess superposition makes sense, but why do you need to use that? Find the equivalent resistance and voltage divider.
Because you have multiple sources in the circuit.
But if you do superposition, then you only have one source and others go to ground.
Yeah, so that's easier to do Thevenin's because you can directly remove that source, short that source to ground, and then look backwards to find out the resistance.
So it's just good practice.
I don't know how to make it work if you have multiple sources and do a Thevenin's. So you have to just have one source in there.
I mean,
Use superposition, don't use Thevenin's.
Just break it up like in this case, find the out based on voltage divider.
Yeah, you can do this one by that, right?
But
by doing that. But
practice because it gets too complicated eventually.
So if you have this circuit, right, for example, you just do superposition instead of converting this guy to its Thevenin's equivalent, right? Yeah. Then you have to. So you have a resistor here, which is in parallel with everything here. So in that case, you have to calculate the resistance here and then make a parallel resistance in order to find out the voltage here. Yeah, it just takes longer time, I think. Yeah. Yeah, for this one, it's a lot easier because these are just parallel resistors. That's right. So because the source is on the right-hand side, you combine these two, you got a 1R, right, and connect to here. So this is 2R, and combine 2R and 2R, you got another 1R, right, connect to here. So got 2R, 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 right? 2R and 2R. Then what's next? It's just a voltage divider. So VL equals VDD over 2. After combine all the resistors, eventually you are getting this. And so eventually you have a digital input 101. Okay, 101 or 101. No, second one. Because D2 is MSB. You want to start with MSB. Yeah, 101, right? This is LSB. And so VL overall, VL equals VL1 plus VL2, which is VDD over A plus VDD over 2, which is VDD over, 5/8. Wait, is that? Yeah, 5/8 of VDD. Okay. So I have a similar homework assignment due Friday this week for this calculating this. It's pretty simple, right? Straightforward. And yes. There's there will be a quiz next week regarding this, I think, or Friday this week. So we have a quiz today and another one on Friday. So I haven't made that Friday quiz yet, but today's quiz will be another superposition, a very simple one. It's pretty much just repeating the ones we did on Friday. So for the IEM, pure play, and service companies, I'm not repeating that anymore. You can find out the answers in the previous videos or just search in Google, right? So we should talk about a little bit more about op-amps. I want you guys not getting confused in the future if you are using an op-amp to amplify a analog signal. Let's do this. Feedback resistor R1, V in, V out. What's the gain, voltage gain for this configuration? Which we were just talking about this. This is the first time you guys got confused. Why V out here equals VP minus VM, AOL, but why here V out equals VI times negative RF over R1. What's the difference? Yeah, the feedback makes the difference. One more question. It can be in the interview. So for the op-amp, if I grab the op-amp from the drawer in the lab, right, it has a pretty good amplification here, which is infinity. Why do I still make a negative feedback to get a finite gain, voltage gain, instead of using a huge gain here? You can control it better. Okay, a lot of times you don't have to amplify it for millions of times. This will saturate the voltage very quickly. And so you use so the open loop gain is always there, right? It's just to derive this closed loop gain to here using AOL, it takes a lot of time. I kind of forgot that how to do it as well. I have to look at my notes in 3 years ago in analog. So we are not doing that derivation, but now here's a conclusion, right? So you got a negative sign in front of the voltage gain, and most of the times you are not doing more than 10 times. So for example, if you got a 10K here, there's a 1K here, it's being amplified, the voltage being amplified by 10 times. So what's the negative sign here being used for? Or what's the effect of the negative sign to the output voltage? The phase. If this is the input, if you're using this configuration, you're getting an output with 180 degrees of phase shift. You should know that. If it is 10 times of voltage gain, one more time. So what is the name of this gain here? What's the name? So the gain here is called open loop because you don't have a closed loop. It's called open loop voltage gain. And this one is called closed loop voltage gain. And if you are having a 10-to-1 ratio, it's going to amplify it by 10 times. So you're getting this. Right? And you were told that the currents are not getting into the amplifier. So the currents flows that way. And you were also told that there's a virtual ground if you ground the non-inverting terminal, and this one will be virtually grounded to ground as well. It's called virtual ground, and the VP and VM are virtually shorted together. It's just so many questions. Why do we do that? If you're virtually grounding that point, and also there's no current flowing into the amplifier, and why is amplifying your voltage? If there's nothing getting into it, why do we still need it? So if we don't have an op-amp here, okay, you just have a few resistors. I'm just redrawing this circuit without an op-amp, the presence of the op-amp. This is RF, R1 is a VI, this is a V out. There might be a load resistor, RL, right? If you connect to something, there must be a load resistor or CL as well. It's just everywhere. This is a load. So if you don't have the op-amp, are you still able to amplify anything? It's going to be a voltage divider. It's going to keep dividing your voltage to a smaller one. You are not able to amplify it. So why is this one is amplifying it? I'm not understanding that answer.
Like I guess my understanding is it's producing an output to try to keep the two virtually shorted.
They are virtually shorted because of the op-amp design.
Yeah.
Mm-hmm.
But if you're grounding the bottom one and putting a voltage to the top one, the op-amp has to like keep that short.
Mm-hmm. Because the design of the op-amp is allowing this one to be dropped to zero really quickly. So you are dropping this voltage to zero really quickly. Before I get the conclusion, let me ask you another question. Is 0 volts bigger or -5 volts bigger in this in the op-amp in this amplifier? Which one's bigger? Which one's the bigger voltage? 0 volts or -5 volts? Look at this. You are amplifying your voltage amplitude. I think I give you another example so you can understand what I'm talking about. So if your left hand is grounded and you are touching a 20,000 volts plus 20,000 volts with a lot of current, infinite amount of current supplying, you will die, right? So what if you ground your left hand and you are touching a negative 20,000 volts? You also die, but in a different direction, right? The current is going to flow in a different direction. You know what I mean? So you touch 20,000 volts on the right hand side, the current is going to flow that way. And you'll die probably that way, right? And if you touch negative 20,000 volts, you got a huge current flowing from ground to negative 20,000 volts. Okay, you'll still die. So what if you touch 0 volts on your right hand side? Even though it's still within that super powerful circuit, but you're touching 2 ground points, you'll be fine. No current, no voltage drop, right? So no current flowing through your body. So my question is 0 volts larger or negative 20,000 volts larger? Yeah. So same here, right? You got your signal amplified. Even though it's swinging backwards, there's still a huge voltage, which will generate a lot of potential difference and pump current through something. Okay, so that's why I want to drop the voltage to the smallest voltage as soon as possible. Okay, and then whatever it's gonna rise afterwards, right? It will be larger than 0 volts. If I have a bigger resistor, I'm having a bigger voltage drop. I'm getting a more negative VL, which is actually a bigger voltage. The current is just flowing that way. You got a 0 volts here, right? Even though the current flows that way and you are getting a negative voltage, but still it's a big voltage compared to ground. The reason that you are getting a bigger voltage or the voltage is getting amplified is because you dropped, or the op-amp just dropped the voltage here to ground really quickly. So you're able to gain some voltage here. Otherwise, it's going to be just simply a voltage divider circuit. Okay. So that's why this one is amplifying the voltage. And there's another name for this configuration. It's called TIA, or transimpedance amplifier. Because it converts current. This is another topic will confuse a lot of people. 90% of the electrical engineers graduate from college cannot answer that, but so it's okay if you're getting confused. So this is a TIA, which means it converts current into VL, into voltage. And we are looking at VL equals VI times this one. Apparently it's amplifying VI with a certain gain to VL. So why is not converting VI into VL? And why is converting current into VL? So this is actually amplifying current or converting a current into a voltage. Is that very confusing, right? It's very confusing, is it? It just couldn't answer that if you don't, do this example. Why is converting current into VL? But your equation here is definitely converting voltage to voltage. Where? Where's the infinite resistance? Oh, here?
Yeah. Right.
Yeah, that's right. Yeah, that's right. Because you have a ground here, right? Virtual ground, which is made happen by the op-amp. So even though you have a voltage here, but the voltage is getting converted into a current immediately. Why is that? Because of Ohm's law. You got a voltage and this is ground. VI to ground, that's a certain voltage drop. You cannot change it. It's already exactly that voltage drop. So you're actually pumping a current into the circuit. So what is a current? It's a VI over R1, or VI minus 0 over R1. That's a current, actually. If you move this equation around, you are finding actually it's minus RF times VI over R1. And this is a current. This is a current. Okay? So this is the transimpedance amplifier because it's transimpedance is converting a current into voltage. And this is the current, and this is the gain. So sometimes if someone is treating this one, the voltage amplifier is okay. But in a lot of cases, this is being used as a current to voltage converter. Is a transimpedance, is a TIA. And the most common application to this one is the camera's pixels. So the photodiodes, you connected reverse biased photodiode. And this is RF, this is VL. In each pixel of your camera, you have an incident light hitting that little photodiode, it's just 1 pixel in your camera chip. Okay, so if some photons hit that photodiode, it's going to generate a photocurrent flowing that way to the ground, from here to ground. Why? Is it because of physics? That's what Einstein found out in 1930s and won the Nobel Prize. So if a photon hit that semiconductor material, it's going to generate a photocurrent. It's just being generated in the semiconductor material magically. Okay, so it's going to draw a current that way. What's going to happen? What's going to happen if it's drawing a current that way? I'm just trying to let you guys think, right? Instead of I'm telling you guys everything. Wait, the current is flowing that way to ground, right? What's going to happen? What's going to happen? Yeah, it's going to be, there will be a voltage drop across that resistor. And the voltage here, the same as here. So you are getting a what? So you are getting what? V out. Is that something you want? Yes, if you got a strong incident light, you got a bigger V out. You got a weaker incident light, you got a weaker V out. So you're getting a brighter pixel on the camera. And V out is the analog voltage or digital voltage here? Analog, right, for that pixel. And then you need what to convert it into a computer understandable ADC. That's how you show something on your phone, right? After you take the picture, if you zoom in, there will be millions of pixels, right? And that pixel, I know it's colorful, but if you're doing it because it has filters in front of it, if you just remove the filter, it's just reporting a grayscale, right? It's from 0 to 255, it's an 8-bit. If it's 14-bit, it's going to be 0 to, I don't know, right? Whatever, huge, right? Okay, so it's going to have all different levels of intensity from black to super white, right? For that pixel. And all that output or the outcome is start from here. You got a photodiode to lay out a diode, basically, with some adjustment to the diode layout in VLSI, the EDA tools like Cadence. Okay, and then connected to the op-amp with a resistor here. And usually this is a gain resistor. It's usually a very big one, like 10 milli or something, because the photocurrent is in picoamps level or femto levels, like 10 femto-amps. So we need a huge resistor here in the TIA to convert it into a readable voltage to the ADC. You can, right? But it's not making too much sense.
How would it work without
No voltage? How do you know there's no voltage? There's an internal resistance over here, right? Depends on the light intensity.
So the information coming out of the end of the diode is just
Definitely there will be, but we are not, because we are using this one purely just for the current as an input. So we don't worry about that one anymore. We are not amplifying, it's not converting a voltage to something. It's directly just a current signal. There's no voltage. If you have a voltage signal, you do need a resistor to convert into current, right? And then use a TIA here. Yeah, the current already automatically, magically is going through RF. It's generating a voltage at the out. So we don't need anything here to convert the voltage. It's not a voltage source. It's called photo effect, right? That's the name of it, photo effect. Okay, So this is called inverse configuration, inverting configuration of the op-amp configuration. And the non-inverting configuration is purely just a voltage amplifier. This one. This is a non-inverting. Because the input is going to the non-inverting terminal. And VL equals VI times 1 plus RF over R1. We're not going to derive it. It's pretty easy to derive it, but we're not going to do that. So VL equals VI times 1 plus RF over R1. And this is not a TIA anymore. It's just a pure voltage amplifier. And the input and output has the same phase, which means your input is like that. You amplified it, it's going to be the same phase. Okay, there's no phase shift anymore because there's no negative sign. It's all positive numbers here for the voltage gain. So if you look at this circuit and the one I just drew on page 4, the feedback resistor is always feeding back the current into the inverting terminal. It's called negative feedback, right? See here? It's a negative feedback and negative feedback. And if you are using this op-amp as an amplifier, you are not feeding this line to the non-inverting terminal ever. And so why is that? So this can answer another question as well, because you were told that these two terminals are virtually shorted together. Okay, it's being caused by the infinite open loop gain. It just seems like I'm jumping here and there randomly, but we'll see it's all connected to each other. I'm going to explain why. So open loop gain is making these 2 points virtually shorted possible. And why? Before I answer that question, let's look at this comparator circuit. Okay, it has an open loop gain. Are these 2 terminals equal virtually? And why? So this could be an interview question, seriously. Because they know that a lot of people don't know what's going on here, right? If you just did the homework assignment in the class using the ideal connection for the op-amp but never manually connected a op-amp on the board and feed the signal into an amplifier and ADC to digitize it, you'll never understand what's going on here, okay? It happens to 99% of the students graduating from a EE major. I'm repeating this question. If you have an infinite open loop gain and you grab op-amp from the drawer in the lab, you were told they were virtually shorted together. Are they virtually shorted in this case? And why? And or why not? Why not? No. I'm going to tell you that answer in a bit, and you should memorize that. It really can happen in the interview. If you are looking for a job like making PCBs or, it happens a lot to us, to our alumni. Finding a job in the national labs, they may ask that question. You should know exactly how you should answer that. The open loop gain is the infinite open loop gain, and I grab this one. They are not virtually shorted. But if I have this circuit, they are virtually shorted, and why? remember one answer, right? Because this one has a negative feedback. And I'm going to explain why negative feedback will virtually short them together. For example, okay, we know that someone designed op-amp is giving this op-amp open loop gain as an infinite number, okay? It's not changing. It's not changing here. It's not changing here. Even though you have a negative feedback, it's not changing. It's still working that way. So we got a VM here and VP here. They are virtually shorted, which means they have a ideally they should be equal, but in real world they are slightly different because this one is not infinite. Okay, so let's see if because I have a negative feedback, if the voltage at this node if this one at some point becomes smaller than VP. So you are getting a tiny little bit of plus number here, right? At some point, VM becomes smaller than VP. It happens really quickly, okay? And times this open loop gain is going to give you a very big VL, right? And VL is going to dump current through this feedback resistor to VM and bring it back up to make it equal. This happens really quickly, keep in mind. Probably in the speed of light. The electrons are moving super fast in conductors. Does that make sense? That's how you prove it. How you make yourself comfortable with that reality here. Okay, so I'm going to ask you a question as an interview, during the interview, okay? So why VP and VM are virtually shorted in the inverting configuration? Close. Just make it simple. I'm going to repeat this for multiple times because it's important for the interviews. Just answer that key question, key answer here. So why VP and VM are virtually shorted, or they are equal? Just answer because of the negative feedback. Okay, just answer that. If they let you explain further, you can say, hey, let's prove it. If this is a slightly smaller than VP, because the open loop gain is huge, right? It's going to bring this back up by dumping current through the through the feedback resistor. It's going to dump current to here to bring it back up. Does that make sense? It's adjusting VM. So VM, VP are like, they're floating a little bit, probably adjusting themselves really quickly. Okay, and this one is a little bit larger than this. It's going to be adjusted by the feedback resistor really quickly, or vice versa, or this way. Same thing. It happens way faster than my hands. So they're always virtually shorted. So for example, what about you have VP a little bit larger than VM, a little larger than VP. You got a very small negative number here. And times a huge open loop gain, you are getting a huge negative potential. It's probably not getting there, but it's trying to. So VL is trying to go negative very quickly. What's going to happen? If VL just at some point, all of a sudden, it's start dropping really sharply, dropping the voltage really quickly. It's definitely not going to drop to the infinite negative number, right? Just start trying to drop, right? As that potential or momentum. What's going to happen? It's going to draw current from VM, right? It's going to draw current from VM and reduce the potential here. reduce it. Because we are saying Vm is slightly larger than Vp, and because of the voltage equation for the op-amp, because Vm is slightly larger, we'll do the quiz next time. So because Vm is slightly larger than Vp, so it becomes very negative, so get a momentum to move downward. It's going to draw current from Vm very quickly. It won't happen that much. It's just happening super quickly. It won't be a lot of current. It's just adjusting it really quickly, so to bring this to reduce the voltage at Vm to make it equal. So it's dynamically adjusting the voltages.
The overall idea of the op-amp is that Vout is changing the positive and negative terminals.
Yes. So you can amplify something, right? Like this case, they are equal because this is 0. You want to make this one to be 0 as well. So you can drop the voltage to the smallest voltage in the circuit. So you can bring it back up to Vout. So you're amplifying it. Okay, make sense? Okay. So keep talking about this topic next time on Wednesday. So see you guys in. Let me see. Let's keep doing that in 2771. What about that? Keep it consistent. Because sometimes someone will use the 602 lab. Then we have 5 people working there. It's taking a lot of space. We have space in 2771. Hopefully they have electric device over there. If you have a laptop, yeah, they should have electric device in there for us to use. Okay. 27.